And for the live example here, I will try to illustrate with the motor systems tool a fixed speed circulator compared to a proportional pressure circulator. And I will start by putting up the curves from before, and then I will start the motor systems tool, which can be found at the motor systems annex homepage, and it's free, downloadable. We also have a webinar where you can learn about the tool, so we won't go into the details today, but we will select a pump system. We will select no transmission, and we will select a standard motor. We don't really know about the motor, but we take a guess that it's a 1.1 kilowatt motor, i.e. 1 in this case. And we have direct online connection for this motor. And then I just have to move the tool, and I have to move the pump curve a little bit so we can see the duty points of this fixed speed motor. And the 4 duty points to use in the compliancy calculation, I have put in the curves. And now I will put in the first duty point, which is, as you can see down here, 1.55 kilowatts. 1.55, and this is from the wall outlet. And I put that in, so you can see the number over here. And also, I can, in the other end, input the hydraulic parameters for the pump, because in this case we have the curves, so we can put them in. And for the first duty point, we have 7.5 meters of head, and we have a flow of 38 cubic meters per hour. When we put these two numbers in, the program automatically calculates the hydraulic power, and when this is known and the input power is known, efficiency is quite easy to calculate, in this case 68%. We say OK, and now we have the first duty point of the before situation. This duty point I will put in the table here, and the first duty point from the 6% running time would be 360 hours, and this is now put in. For the second duty point, we have input power, measured input power of 1.45 kilowatts, and we have an hydraulic output power of, in this case, 10.5 meters of head, and we have a flow of 28.5, and in this case we get another efficiency calculated, and this is our second duty point. We will add this line. We have, in this case, 900 hours per year, and this is now added. The third duty point is 1.25 kilowatts, and the hydraulic parameters would be 12.4 meters of head and 19 cubic meters of flow. We have the new efficiency calculated, and we put it in, and we add this line, and in this case we have 2100 hours per annum. And the final duty point, we have an input power of 1 kilowatt, and the hydraulic output of the fourth point is the head of 13.75 and a flow of 9.5, and we have the new efficiency, and this is the fourth duty point. We add it to the calculation. In the fourth point we have 2,640 hours, which is 44% of the 6,000 we talked about. And now we have the complete before situation in the red scheme. If we go to energy calculation, you can see in the curve of duration how the energy consumption is distributed from this system. A total of 7,128 kilowatt hours per year is the result. And now we will input the after situation. The after situation is a pump with proportional pressure control. It's also a system where we put in a standard motor which is better than the old motor, so now we put in RE3 and we say OK, and we say OK, and then we have the first duty point, and the first duty point you can see from the curve have an input power of 1.25 kilowatts, and the hydraulic parameters of the first duty point in the new system is we have the same, we have a head of 8 meters in this case, and then we have the same flow as before, which is 38 cubic meters. We get the efficiency calculated, and this is okay. So this is our first duty point of the after situation. We add the line. The first duty point had 360 hours, and this is now put in. We take the second duty point. We have 0.8 kilowatts in input power. The hydraulic parameters of the second duty point is 7 meters of head and 28.5 cubic meters of flow. We add this line for the second one, which is 900 hours. And then for the third one, we have an input power of 0.45 kilowatts. We have an output hydraulic parameters of 6 meters of head, and we have a flow of 19 cubic meters. We get a new efficiency. Okay, and then we have the third duty point, and there we have 2100 hours per year. And the last duty point in this case would be 0.25 kilowatts, and the hydraulic parameters in that case would be 5 meters of head, and it would be 9.5 cubic meters of flow. Okay, and we add the line, and in this case we have 2,640 hours in the fourth duty point. So now we have the complete after situation in the green table. We have the complete before situation in the red table. So when we push the energy calculation in the motor systems tool, we can, in this case, see that the red curve is the before situation, the energy distribution before, and the green one is after, and we clearly see the difference between the two curves, which is the summarized energy savings in this case. So from 7,000 kilowatt hours, we now have a little less than 3,000, so we have more than 4,000 kilowatt hours per year saved in this specific situation. Of course, it can be discussed how the duration of the hours and so forth in real life, but this gives you an idea of the savings, at least on a theoretical level. Okay, so thanks for watching, and hope that you will. I hope you will use the Motor Systems tool, because it's a very easy, accessible tool, and can provide you with answers in a quite simple way when you learn to handle it. Okay, thank you for this, and yeah, talk to you another time.